In this question, we have 4.50 grams of methane gas occupying a volume of 12.7 decimeter cubed, or liters, at a temperature of 310 Kelvin. It undergoes an isothermal expansion against a constant external pressure of 205 Torr. It is a closed system, so N2 is equal to N1. We are told that it undergoes an isothermal expansion until the volume increases by 3.3 decimeter cubed. And so V2 is equal to V1 plus that marginal increase. And it is isothermal, so T2 is equal to T1. In this question, I think that we can determine all of Q, W, delta U, delta H, delta T, delta V, and delta P. And it doesn't matter what order we do them in. Well, I suppose it does. We'll need to do them in an order that makes sense, but we don't have to do them in the order that they're asked here or listed. So once again, what was given in this question is that it's methane gas in a closed system, 4.5 grams, 4.50 specifically, occupying a volume of 12.7 decimeter cubed, which we know are liters, same unit, at a temperature of 310 Kelvin, so there are two significant figures on the temperature, undergoes an isothermal expansion against a constant pressure of 205 Torr until the volume changes by 3.3 decimeter cubed. And we're asked to find all of these things. All right, so we need to make an assumption here because we're not told that this is a real gas, we're not given a compression factor, and we're not given any van der Waals constants. We're told that it's a van der Waals gas. And so we are going to assume that methane is behaving as what? A perfect gas. That allows us then to use the equation of state for a perfect gas, which is that PV is equal to nRT. I want to be able to use this as a true relationship. All right, which one of these are you going to determine first? Which one, in fact, is known? Well, it's isothermal. Okay, so let's check that one off. It's isothermal. Therefore, delta T is equal to 0. Now, not only is it isothermal, but it's isothermal and perfect. And we know that when a system is perfect gas and undergoes an isothermal change, so we have the conditions of isothermal and perfect, we can say therefore that the internal energy change is nil. It's equal to 0. Okay, so now we have that one taken care of. Now the first law always applies. So I know that du is equal to dq plus dw. But we just said that the change in internal energy is equal to 0. Therefore, I know that if this thing is going to expand and do work, then heat and work have to be equal and opposite for this change to occur. If there's no change in internal energy of the gas and no change in temperature, but yet it's doing work and therefore energy is leaving the system as work, an equivalent amount of energy must be entering the system as heat. So when I find one, I'll have found the other. So I'm not going to circle these quite yet because they don't have their numerical values. Well, which one would you consider the formulation for to continue this question? dq over dt is equal to a heat capacity, so dq would be equal to a heat capacity times dt. That's not going to get anywhere because it's constant temperature. Let's look at work. dW. I know that dW is always equal to a minus pdV. Now that's going to integrate differently depending on the kind of question that this is, or the kind of change actually that's going on. And in this change, I know that it's against a constant pressure of 205 torr. And so I know that dW is equal to a minus P external dV. And so my work, which is equal to the negative value of Q in this case, is equal to the integral of dW. And that's equal to the integral of minus P external dV. Do you have to show all this each time? No. I'm just drawing this out because it's a tutorial. And so work, because that's what that is going to equal, let's skip a step here, or at least do it out loud. This is a constant external pressure, so it's coming out in front of the integral sign. And so work is actually equal to a minus P external integral of dV, which simply integrates as delta V. So my work is equal to the negative P external delta V. And my delta V, remember, it said that the expansion occurred until the volume changed by 3.3 liters or 3.3 decimeter cubed. So that's great, I know it. And it also was working against, you look back in your notes, 205 torr. So I have a minus 205 torr. Now think about this before we write anything else. The external pressure is in torr, and this is in decimeter cubed, or liter. Let's call it liter. So my work is going to be in units of liters times torr. And I really want liters times atmosphere, because then I can use my 101.3 conversion factor to get it to joules. So in this same equation, I'm going to convert, and that one is exact, so that's not limiting my answer to 1 sig fig. 1 atmosphere is 760 torr. So that'll get my pressure to atmospheres. And then I'm multiplying by a delta V. So I could determine V1, and V1 is given as 12.7, and I could determine that V2 is that plus 3.3, but really I'm just after the delta V. And so this is multiplied by delta V, which is 3.3 decimeter cubed. That's what was given in the question. And of course I know that a decimeter cubed is a liter. Now before we swing back over here, torr, atmosphere, I'm going to be left with liter atmosphere, and so I want to convert that all in the same solution line, that I have 101.3 joules per liter atmosphere. What that allows me to do then is to demonstrate nice and clean and clearly within the question all of my unit cancellations. Torr, atmosphere, decimeter cubed, liter, and I'm left with joules. And so work is equal to a minus, now whatever this is, and so we'll get our calculator out. And you can do this along with us. That's 205 times 3.3 times 101.3 divided by 760, and that's the only thing on the bottom. I get a minus 90.17. And that's in joules. The number of significant figures here should be 2, and so work is equal to a negative. Now how are you going to represent? It's just 90. You could put 90 with a point, a decimal point, and that would keep the two significant, the two figures significant, or I can just say 9.0 times 10 to the 1. So using scientific notation is always a really good way of clearly listing the correct number of significant figures. And therefore, Q, which is supposed to be equal and opposite, now I've got that answer as well. And so my Q will be equal to the positive value of that 9.0 times 10 to the 1 joules. So what have I got to calculate left here? I just did this and I did this. I need delta V. Delta V was given 3.3 decimeter cubed, or liters. So I just wrote that down. I need a change in pressure, and I need a delta H. Change in pressure. Okay. It is a constant pressure change, but I'm just wondering, what was the pressure here? See, I'm actually given enough information. If I use 16 grams here per mole, and get the number of moles, and I'm assuming that it's perfect, so PV is equal to nRT, I can actually find my initial pressure before it was changed to 205 on the outside, 205 torr. And ultimately, the final pressure is the same as that which it expands against, remember? So let's do delta P, and then we have to do delta H, or we could get delta H out of the way right away because it's easier. So let's do that one right away. I'm circling it before we actually get a numerical answer. Now, the thermodynamic definition of enthalpy is U plus PV, and that's always the case no matter what kind of change we're looking at. And so delta H is equal to delta U plus delta of this PV. But I can also write that as, because PV is equal to nRT, delta U, plus the change in nRT, which would be N1RT1, say again, N2RT2 minus N1RT1. Well, that is constant, and so is T constant. And so nRT is a constant for the process. So is PV a constant for the process. So in fact, this is 0. We stated that already. And this is 0. We just found out. And so therefore, delta U is, that should have been H. Therefore, delta H is equal to 0. Okay, now we're after a delta P. Well, delta P is equal to P2 minus P1. But we know that the final pressure is equal to the constant external pressure against which the expansion occurred. And so P2 is 205 torr. And so I really need to know what P1 is. Again, the gas is behaving perfectly, and so I can write that PV is equal to nRT. And in the case of the first equilibrium state, and isolating for P, I have that P1 is equal to nRT. It's isothermal, so T1, T2, N1, N2. I don't need all of the subscripts. Divided by V, and that would be V1. And so that is equal to, okay, I'm just going to use 16 grams per mole for methane because I only need two significant figures. But if you want, hydrogen is 1.0079, and I've got 4 of them, and I'm adding 12.01. So it's 16.04. Okay. my mass. I had 4.50 grams. I need to convert that to moles, and we just added that up. 1 mole is 16, or if you want, 16.04 grams. So there's my N. The R value I'll use is 0.08206 liter atmosphere per mole Kelvin. The temperature T1, or throughout because it's isothermal, was given 310 Kelvin, and that is all over V1, which is 12.7 decimeter cubed, which is also a liter. Grams, grams, moles, moles, Kelvin, Kelvin, liter, liter, and I'm left with atmosphere. That's fine, I can change that one to atmosphere as well. Or how about this? Because that's in Torr, why don't I change this one to Torr? 1 atmosphere on the bottom, 760 Torr on top, because it didn't ask for a specific unit value of delta V or delta P, so I'll just keep mine in Torr. Okay, so calculator again, 4.5 times 0.08206 times 310 equals, and then divided by 16.04 on the bottom, that's 7.136, and now I'm going to divide by 12.7, and so it's 0.5619, but that's atmospheres, and so we'll multiply now by 760, and we get 427. So P1 is 427 Torr. And to 2 significant digits, P1 at 7 will make that a 3, so 430 Torr. And therefore delta P, which is P2 minus P1, P2 is going to be a negative value. We had a pressure drop. 205 minus 430. And I'll put the unit outside. And that'll be a negative 225 Torr. I have a 5. So I'm just going to say 220. Keep it even. Okay, so there's delta P. So that's a good question. We were able to, with just a little bit of information, calculate the heat, the work, the changes in internal energy, enthalpy, temperature, volume, and pressure for this change. This change was an irreversible one that happened to this gas against the constant pressure of 205 Torr, isothermally at 310, from an initial volume of 12.7 liters until the volume changed by 3.3. It was closed, no gas leaked in or out, and it was methane behaving as a perfect gas.